All right, I think we're live. Hello everyone. I'm Samir. I'm a first year at MIT, and I'm helping organize HMMT education. We're very excited that you're joining us today for this class from Jeffery Yu about algebraic number theory. So I'd like to begin by sharing a couple logistical rules. You can use the Q&A feature to ask questions, so don't use the chat to ask questions. And you can also upvote other questions you think are interesting. I'd like to remind you that Jeffrey is taking time out of his own day to join us, and we're very grateful for that. So please be on your best behavior and be respectful of the teacher, this classroom, and your peers. And we can remove you if you're being disruptive. So please don't abuse the privileges of being able to ask questions. Now I'll briefly introduce Jeffrey. He's a junior at MIT studying math and physics. He specializes in number theory and quantum information, but he has very broad mathematical interests. And yeah, so now thank you again for coming, and I'll pass it off to Jeffrey.
All right, great. So I'm going to share the board. Let's see, does this show up all right for everyone?
Yep.
All right, great. So, all right. So yeah, I have the Q&A window open. So if anyone has questions, feel free to type in and I'll see them. Yeah, I don't think it should be blocking the screen share, the Zoom windows, but let me know if something looks grayed out or blocked. All right, so yeah, I guess I'll get started. I imagine a couple more people will trickle in, but let's get started. So this is a talk about number theory beyond the integers. I'll probably post either a copy of this board on my MIT webpage afterwards, if people are interested in reviewing it, and I'll probably also write up some notes about this in the upcoming month or two. Currently on my webpage, I have my talk from last February's HMMT education event. That was a completely different talk about integrals, but you can check that out if you're interested. And yeah, so some notes and versions of this talk will be available on there if you want to look back on it afterwards, or if you want to share with your friends who weren't able to attend this talk. And I think this talk is also being recorded if you want to view the recording later. All right, so throughout, I think, throughout middle and high school, throughout a lot of math competitions, a lot of the number theory you see focuses on integers, right? And that's our starting point. We have our integers, and even though a lot of the problems you think about are just deal with positive integers, we want to consider both positive and negative integers, right? And so this is sort of the starting point in number theory, but number theory is actually much more than just about integers. And I want to share with you some of the other types of numbers we study. So first I want to talk about how we construct. Someone can't hear me. Can other people hear me?
Yeah, I think it's fine.
Okay, yeah. Yeah, so maybe the person who asked that question, just check your audio settings. All right, great. So let's see, what was I saying? So we want to construct new sets to try to apply number theory techniques to. And so what are some other sets that you might have already encountered throughout competition? So you might have not consciously thought about this, but polynomials you actually can do number theory on polynomials. So we denote this set by the bracket x, and I'll just explain the bracket in just a moment. Right. So these consist polynomials of finite degree. So you have coefficients, and x is a free variable here, right? And then k is going to be some natural number, and then your coefficients will be in the integers. So these are your there you go. Yeah. So these are your ordinary polynomials, and you've probably done various number theory problems that involve factoring polynomials and studying with primes and stuff like that. But this is a general operation And this bracket here is what we call adjoining something. So what this means is we started with the integer z, and then we introduced a new variable, in this case x. Here x is a free variable. Then we considered all sums and products of integers with x and stuff like that, right? So this is the most general form of a polynomial. You can add and subtract polynomials together, and you can multiply different polynomials together, and you'll get new polynomials, all with integer coefficients. So this was an example of adjoining some abstract variable x. You can also adjoin more concrete things. So for example, one of the things we'll study today are the Gaussian integers. And the Gaussian integers arise from when you start with the integers, and then you adjoin the imaginary number I. Okay, so a couple ways of thinking about this. One way is you could think about substituting I for x in this expression, seeing what kind of numbers you get. Another way of thinking about it is you just start with the integers, you introduce this new imaginary number I, then you ask what can you get from multiplying, adding, subtracting these things together. And if you just think about it, you'll see that you can get numbers of the form a plus bi, where a and b are integers. Right? The idea is because I squared is -1, then you can separate out the even odd degree terms based on real and imaginary parts, which will all contain integers. So that's why a and b are integers here. Another set of numbers we consider, we can adjoin other stuff. We can adjoin things like square root -2. So this is I times the square root of 2. And of course, this squared is going to be -2. So then you can separate out things based on their real and imaginary components. But I can actually be more specific than just some in terms of I. I can write this as a plus b root -2, where a and b are integers. Okay, these are the sorts of objects we construct in number theory. We start with the integers, and then we add some new numbers that aren't already in the integers, and then we try to apply number theory techniques to the resulting sets. Now, these sets are more abstractly called rings. And in abstract algebra, there's a technical definition of a ring, which I'm not going to describe. You can look it up later. It's not too interesting. But the important point I want to talk about is that rings are basically sets where you can do addition and multiplication. Addition and multiplication. Okay, and they have to satisfy certain properties. So everything needs to be commutative. You need to have associativity. Multiplication needs to distribute over addition. But don't worry about those. The important point is that it has addition multiplication, has a 0 and 1. So it has an additive multiplicative unit. And the other important point is that addition is always invertible. So if you have some number, you can take the negative of that number. And when you add a number and it's negative, you get 0, which is the additive identity. But multiplication does not have to be invertible. Multiplication might not be. Okay. And because multiplication is not invertible, we don't want to talk about division, right? Division is a dangerous thing. What math drawing software is this? I will answer that question at the end. I can talk about that. I think since this is the last class, I can probably go a little bit over answering questions at the end. So I'll save that for the end. Yeah, so let's see, where was I? Yeah, so I was saying that we want to be careful with division. We can't always divide. And because of that, I don't want to talk about division at all, really. So I'm going to reformulate any statements involving division, which are bad, into statements involving multiplication, right? So we can freely talk about subtraction. That's not dangerous because addition is invertible. So, but we want to talk about, we want to translate what we think about as statements of division into statements of multiplication. So for example, when we say we want to divide by n, this is dangerous because we can't always do this. So the correct thing to say is we're going to multiply by the inverse of n if it exists. Right? And the if it exists is important because it doesn't always exist. And so you might ask, when does it exist? So we say something is invertible multiplicatively if 1 over n exists, right? But when we write fractions, that's sort of implicitly saying division. So we're gonna try to not think about it like that. We say something is invertible if there exists some other number, exists m in whatever set we're working with, such that n times m is 1, right? So this is basically m is the inverse. When you multiply it to n, then you get the multiplicative identity. And another example is divisibility, right? So when you normally think about divisibility, you say a divides b, or b is divisible by a if b over a exists, right? Over the integers, you would say b divided by a is an integer, but this involves division. And the better way of saying this is to say there exists some number m in a ring such that b is equal to a times m, right? You see, so the left and right side are all equivalent statements. But because in our generic rings, which are sets with addition and multiplication, we don't have division. We want to formulate everything in terms of multiplication when possible. Okay. Now, so I've talked a lot about things not being invertible, but sometimes things are invertible, and that's nice. So we want to be able to talk about what is invertible. So things that are invertible are called units. So units are elements of a ring with multiplicative inverses. Multiplicative inverse. Okay, so let's do some simple examples. So for example, we can say what are the units of the integers? So we normally write this as the symbol for the set with the times symbol on top of it, indicating it's related to multiplication and that you can invert it. So the units in the integers are just 1 and -1, right? They're each their own inverses, and nothing else is invertible. You can ask, what are the units in the Gaussian integers? So in here, you would have plus or minus 1 as well as plus or minus I, right? Because I times negative I is 1. So I and negative I are their respective inverses. Okay. And let's take another example just to get used to the wording. The beginning part will be a little terminology heavy, but afterwards, there's not going to be that much new terminology. So I'm just defining these terms so that we can sort of speak with a common mathematical language. We can let's consider integers modulo 12. This fancy notation means we're taking the integers and modding out by 12. So I imagine modular arithmetic is something you've all encountered throughout competitions. And when does a residue class have an inverse mod 12 in this case? Right. So we know that in general, an inverse exists when the number is relatively prime to the modulus. Right. So mod 12, this would be 1, 5, 7, and 11. Right. In this case, each of these are their own inverses. For example, 5 times 5 is 25, which is 1 mod 12. So 5 is a unit, and likewise for the other. Right. So I think I'll leave it there for examples with units. The last term I want to define in terms of these sets are what we call integral domains. And sometimes in the literature, people just call them domains without the word with the word integral being implicit. But integral domain is basically a ring with the property that a times b equals 0. Let's write that neater. A times b equals 0 implies a is 0 or b is 0. Okay. So for example, in our mod 12 example, this is not an integral domain, not a domain, since you can take two non-zero elements, 3 times 4, and this gives you 0 mod 12, right? And I guess you write this as a congruence normally. So if we've taken two non-zero elements and got 0, so that makes it not an integral domain. And the examples in the rings we're studying today, integers, polynomials, Gaussian integers, these are all integral domains. I think you can probably see that pretty easily just by, I guess, thinking about it a little bit. Now, what I want to mention about integral domains is that in an integral domain, the idea is you can there exists some kind of cancellation property. You can cancel stuff. Okay. So in particular, this, let's see, how should I write this? If a times b is a times c, then it is you can cancel a from both sides. But it's important that we get this right. You're not dividing by a because the inverse of a might not exist, right? So for example, or let's just write this out. So the way we cancel formally is we rewrite this as a times b minus c equals 0, right? And then that means either a is 0 or b minus c is 0. And so if a is not 0, then you get b equals c because b minus c is 0. If a is not 0. Someone asks, 1 is always a unit, right? Yes, that is correct. 1 is always a unit because it's its own inverse. One of the properties of a ring is that, 1 is by definition the multiplicative identity. So 1 times anything is itself. Okay, so I think that's mostly it in terms of definitions for the time being. There'll be a couple more later, but they won't be as bad. So now we've constructed some of these new sets, which we're calling rings, and we have some things to have some ways of describing their properties. So now the next thing, once you sort of, if you're studying number theory from the ground up with the integers, you define the integers, and then at some very soon early on, you start thinking about primes and prime factorizations, right? And one of the most important parts about working with integers as opposed to, say, algebra problems over the real numbers is that you have the idea of prime factorization. Right? Prime factorization exists. And so there's actually a formal theorem telling us that. You may or may not have heard of the formal theorem itself. I'm sure all of us know that prime factorizations exist. This is called the fundamental theorem of arithmetic. Should not be confused with the fundamental theorem of algebra. Right? So the fundamental theorem of algebra tells us that polynomials have complex roots. If, the formal statement would be like every non-constant polynomial with complex coefficients has a root over the complex numbers. But here we're dealing with the fundamental theorem of arithmetic, which formalizes the notion of prime factorization. Okay, so the version we're probably used to is that every positive integer can be uniquely written as a product of primes. Now, the statement as I've said it and as I'm about to finish writing it is not quite correct. There are a couple of technicalities that I want to talk about. So for example, so the notion of prime factorizations, for example, right, 60 is 2 squared times 3 times 5, right? But you can also be silly and write it as 2 squared times 5 times 3. And these are technically not different expressions, but they're obviously the same thing, and we want to consider them to be the same. So we're going to add a caveat saying up to order. Right? So we don't care about the order of the primes, but the set of primes and then the number of each has to be the same. And the other technicality is I'm just going to say greater than 1 here. You can argue about whether the prime factorization of 1 is just the empty set or not. I don't want to really get into that argument, so we're just going to include the greater than 1 caveat here. Right? The idea is that 1 is not divisible by any prime. Okay. Now this is over positive integers, and sort of the positive integers alone aren't good enough because sort of positive integers or the natural numbers don't give you an actual ring because they don't have additive inverses. And even though when we do number theory problems, we normally think in terms of positive integers, really subtraction appears all the time. So we want to be able to account for negative integers. So let's try to write a new statement over Z. Okay, so I'm going to sort of rewrite the same thing, but making it more general over Z. So every, so obviously there's going to be some exceptions, so I'm going to leave some space for the exceptions. We'll talk about the exceptions later, but every integer can be uniquely written as a product of primes. And we already know that order is one of the things we want to rule out. We don't care about the order. Okay, but once I allow for integers, there are new things that come up. For example, I can be even more silly and write it like this. This is perfectly valid. Now you might question whether or not -2 is a prime number. If you're going by like the middle school definition of a prime being a number where that's only divisible by 1 in itself, then you might argue that -2 doesn't work. But then I would argue that 2 itself doesn't work because 2 is divisible by -1 and -2, which is just silly. So we're going to have a better definition of prime in a little bit. But for now, I'm just going to say, yes, these negative numbers are also primes. So we obviously don't, so this is also silly, right? The idea is you can sort of extract the negative signs out front and cancel the negative signs. So we don't really want to deal with signs. Let's just say up to order and signs. We don't care about that. Now, what are the issues here? Obviously, plus or minus 1 is an issue. So let's say not plus or minus 1, right? 1 is an issue, and because we sort of don't care about signs, negative 1 is also an issue. And then there's also another issue, which is 0. So I'm separating these two out because they're issues for different reasons. Plus or minus 1 is an issue because they're not divisible by any prime. 0 is a different issue because 0 is divisible by every single prime. So they're both sort of issues, but for different reasons. Okay, so that's over. So this is the correct statement over the integers. So now I want to ask what happens over the other rings we're working with. So let's start by talking about polynomials. We're used to factoring polynomials. I mean, you've probably been factoring polynomials since middle school in algebra class, right? So normally when we think about polynomials, probably used to thinking of them over the real numbers, but you can do number theory problems with polynomials. Right? You can factor things quadratics. Let's say this is what, x minus 2 and x minus 3, right? You can also be silly and factor this as 2 minus x and 3 minus x. And of course, these are the same. Right? We taking into account the up to order and signs condition here, just put a -1 in everything. So in a sense, we have a way of decomposing larger polynomials into smaller ones. But when we think about factoring, I think most of us don't call these things primes, right? We factor stuff, and if we can't factor it further, then the word we use is irreducible, right? That's the common terminology. And if you have something else that's not factorable over the integers, what's not factorable over the integers, like +1, right? So these things are what we would call irreducible. You can't break them apart further. So we're trying to find the building blocks of polynomials, just like primes are the building block of integers. So now, if you study more abstract algebra, turns out that these are what we call prime ideals in rings. But I'm going to try to avoid talking about ideals today because those are more complicated. So I want to reconcile this notion of primes versus irreducibles, right? In some sense, over the integers and polynomials, we have some sense of what the building blocks should be. So the correct definition of irreducible, which I'll write here, and while I'm writing this down, I guess I'll just mention, if you haven't noticed, I'm going to use the left half of the board for keeping definitions and main results, while I'll scroll on the right half of the board as we do more scratch work and proofs and writing stuff. So an irreducible is a number A. So an A is irreducible means that A equals B times C implies B or C is a unit, right? And so the idea is, because units are invertible, you can put units in everywhere, wherever you want, and you can put them in, toss them out. They don't matter because you can always invert them away. So this is saying that I should mention A itself cannot be a unit. So yeah, a non-unit A is irreducible if you can't break it apart into two non-units. Okay, so like for example, on right here with x squared minus 5x plus 1, you could of course write this as -1 times negative x squared plus 5x minus 1, but that's just silly because -1 is a unit. That's why we have the definition. So actually, now if we think about back to the definition of primes you might have learned in middle or high school, and they're used to in math competitions, with even if you say like a number is prime if its only divisors are plus or minus 1 and plus or minus itself, that's actually the definition of an irreducible, the proper definition of irreducible. So what is the proper definition of prime in a ring? So a prime element, P, means, the correct definition is that P divides B times C implies P divides B or P divides C. This is the correct definition of prime. I guess we also need non-unit here. Okay, so in a sense, your mathematical journey in number theory may have actually been a lie up to this point, in that the definition of prime that you learn, whether it's through school or through preparing for competitions, is actually you learn the definition of irreducible. And if you sort of try to prove number theory from the ground up, this prime property of what you call primes is actually something you prove along the way. Okay, so in fact, I guess I'll write this down, is that over integers, all irreducibles are prime. Okay, but it's not always the case that all irreducibles are prime. And I want to talk a little bit more about the relationship between irreducibles and prime. So here's a general proposition. Proposition is something like a theorem, but a little, I guess, less big of a result. All primes are irreducible. Okay, so what I'm saying is all primes are irreducible, but I'll show you later that not all irreducibles are prime. So there's a distinction there. So here's a proof. The proof is not difficult. Let P be a prime. So in a lot of higher math, some of the basic proofs fall are what we call sort of definition bashing. You want to keep track of what you know and what you want to prove, right? So when I say let P be a prime, that means it has this property of a prime. And we want to prove it has the property of irreducibility. So to prove that, we're going to say, suppose P equals B times C, then we want to show that either B or C has to be a unit, right? Whenever I say or, it's inclusive or, so it could be both, but at least one of them. So here's the idea. If these two things are equal, then P has to divide B times C, right? If two numbers are equal, then certainly each one has to divide the other. So P divides B times C. So this is where we use the property of it being prime, which means P divides B or P divides C. Okay, and if you have some experience in proof writing or Olympiads, this is where we normally make a statement called without loss of generality. What this means is that one of these has to be true, but it doesn't really matter which, right? So we can say if P divides B, then blah, blah, blah. And then you might imagine coming back and writing the proof again, saying if P divides C, then blah, 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 blah. But really they're the same thing. There's no distinction between B and C. So without loss of generality means that it doesn't matter what I pick. The proof is the same either way. It's just a different letter. So we're gonna, for the purpose of not writing the proof twice, we're just going to say without loss of generality, P divides B. So what does divisibility mean? Then there exists M such that B is equal to P times M, right? That's what divisibility means. So then we're going to substitute this back into our original equation. So P is equal to P times M times C. And because we're only working with integral domains, we can cancel P to get 1 is equal to M times C, which implies C is a unit, right? Because M is now the multiplicative inverse of C. So if I know they had P divided C, then we go through the same step, replacing B with C, and we would determine that B was a unit instead. But the proofs are the same. I'm just trying to not write the same thing twice. Okay, so this shows that all primes are irreducible, but I imagine not all irreducibles are prime. So what is an example of this? Let's show this simple example. Irreducibles might not be prime. And so in order to give an example of this, we have to look somewhere beyond the integers. Actually, all the rings I've written down on the left-hand side satisfy where all irreducibles are prime. An example of where this is not true is if I adjoin square root of -3. So in Z adjoin root -3, what happens? Then I claim 2 is irreducible. This is something you can just check, not difficult. Maybe I'll talk about a little bit about that afterwards. But let's show that 2 is not prime. So in this case, 2 divides the product 1 plus root -3 times 1 minus root -3, right? By difference of squares, this is just 1 plus 3 is 4. So 2 divides 4, but 2 does not divide either of these factors, right? You could just check by like real and imaginary parts that this doesn't work out. And 2 does not divide 1 minus 1 minus 3. So 2 is not prime, but it is irreducible. And the way to check irreducibility, that you can't decompose it into non-units, is by using something called the norm. So the norm of, you're probably familiar with the norm of a regular complex number, right? A plus bi is a squared plus b squared. So if you're doing, oh, I'm off the screen. Oh yeah, sorry, I missed the question. Yes, yeah, in order to cancel the p's, though, you need to be an integral domain. Yes. So we're only working with integral domains for the rest of this talk. So yeah, but yes, absolutely. So yeah, as I was saying, what was I? So yeah, this is something called a norm, right? If you're working with geometry of the complex numbers, you're probably used to seeing the magnitude of a complex number being the square root of this. We're going to take the square of this, and reason being is that I want this to be an integer, right? In fact, this is a non-negative integer. Okay, so a norm, more generally in mathematics, is just a function mapping numbers to numbers that's non-negative and satisfies the norm of a product is the product of the norm, right? So in real numbers, you can just take the absolute value. You could, if you want it to be consistent with this definition, you could take it to be the square if you want. But really, that doesn't matter. The idea is you need some notion of size. So this is the norm over the Gaussian integers. If we want a more general norm over other imaginary quadratic rings, I can take something like a plus b square root of minus d, right, for an arbitrary minus d. This will be a squared plus d times b squared. And we construct it like this in order for it to be multiplicative. That's important. Okay. So if you adjoin a ring with something, what conditions does that have to satisfy so that the adjoint is also a ring? Okay, so when I say adjoin something, by definition, so if we look up here, when I say definition of adjoining something, this is always a ring, because I'm considering all possible sums and products. So when I adjoin a specific number, you can think of it as like substituting that number into the variable x and seeing what possible numbers result from it. So I can sort of, by the way we're constructing what it means to adjoin something, when you adjoin something, you always get a ring. Whether you get an integral domain or not is a different matter, and maybe I'll touch on that in the end instead. Okay. So what was I? So yeah, so the norm gives you some notion of size. If you try to just apply the norm to 2, you can't break it down that much further. Over polynomials, the notion of size would be you would use the degree instead, right? So when you factor 2 polynomials, you factor into smaller degree terms. The degree is not quite a norm, but that's okay. All right, so okay, we've seen that all primes are irreducible, but not all irreducibles are prime. So we can ask, when are they the same, right? And it turns out when they're the same, then that's what gives us unique factorization. So let's make a quick definition. So we say something's a unique factorization domain. And so this is why I'm sort of tossing out the question of integral domains, because we're only going to consider integral domains here. It's a domain where there's 2 conditions. One is all irreducibles are prime. All irreducibles are prime. And the second condition is, might seem mysterious, but it's there for technical reasons. All elements can be written as a product of finitely many irreducibles. So the second condition is telling us we can decompose it somehow. right? And then if you have the first condition, then that's what tells you it's going to be unique. So the second condition might look scarier than the first condition, but actually, for all the rings we're studying that involve concrete numbers, the second condition is automatically satisfied. That's actually the easier one. The harder one to show in general is the first condition. Second condition is only here because if you study ring theory more broadly in abstract algebra, you can get very exotic rings where you can't actually decompose it in finitely many steps. But for the concrete rings with concrete numbers that we're dealing with, this is not a concern. So theorem is in a unique factorization domain, we have unique factorization, hence the name. So every non-zero non-unit. So this replaced the not plus or minus one condition I had above. Non-unit element can be uniquely written as a product of primes, as a product of primes up to order and units. So whereas over the integers, I said up to order and sign, the generalization of that is to say up to order and units. Okay, so in this case, plus or minus one of the units over the integers. Over imaginary numbers, you have plus or minus I as well. So that lets us avoid silly things like saying, 5 on the one hand is 1 plus, oops, that should be an equal sign. 5 is 1 plus 2i times 1 minus 2i, but you could also write this as 2 plus I and 2 minus I. They look different, but they're actually related by factors of I. If you take 1 minus 2i and multiply by I, then you get 2 plus I, and vice versa for the others. So we consider those actually the same factorization. So now I told you that, so when the two conditions are satisfied on the left here, then we have unique factorization. So the next question you might ask is, how often does this occur? And the answer is actually, unfortunately, not that often. So here's a fact. So all the rings I've written above, so integers, polynomials, Gaussian integers, adjoining root minus 2, are all UFDs, unique factorization domains. However, if I adjoin any larger number, negative n, for n greater than 2 is not a unique factorization domain. And the way you show this is by having some similar argument. Basically, you just construct something that's irreducible but not prime when n is greater than 2. So that's kind of unfortunate. But rather than dwelling on the unfortunate, which is actually a huge part of algebraic number theory, is trying to figure out what happens when you don't have unique factorization, I want to spend the last, I guess, 5 or so minutes talking about the great things we can do when we do have unique factorization. So, for example, we can ask, what are the primes? What are the primes in the Gaussian integers? Let's see. There's a Q&A. Why am I using square root minus n versus square root n? Good question. So I think it's because most people will think of n as a positive integer. So I want to stress that these are imaginary quadratic fields here. No, I can also consider joining square root n for positive n. But the behavior of those is actually pretty different because something like square root of 2 is actually real. And so the behavior of imaginary quadratic adjoining square root of negative n versus adjoining square root of n, they're analogous statements, but they behave somewhat differently. So I'm just focusing on negative things for now. All right, let's scroll down a little bit on here. So what are the primes in the Gaussian integers? Let's just state these. So it turns out these are integers, and this is something you would prove if you're in a class studying number theory and approaching Gaussian integers and stuff like that. I'm just going to tell you the results. It's primes p congruent to 3 mod 4. It's a plus or minus bi, where a squared plus b squared is equal to an integer prime, right? And by just look at possible quadratic residues mod 4, this is always going to be 1 mod 4. And that's why we sort of split up the 3 mod 4 condition. And actually, there's another one, which is 1 plus I. So we take 1 plus I separate from the a plus or minus bi case because 1 plus I and 1 minus I are associates, because 1 minus I is just like negative I times 1 plus I. So they only differ by a unit. So these are the primes. So we can use these to solve problems. Let's solve a problem. Let's say I'm going to solve, let's solve x squared plus 1 equals y cubed over the integers. Okay. So if you weren't familiar with Gaussian integers or number theory with imaginary numbers, what you might do is you might consider an approach where you try to factor x squared equals y cubed minus 1, right? I mean, factor is y minus 1, because factoring, if you can factor stuff, then number theory lets you sort of use prime factorizations and stuff like that, especially when you have a unique factorization domain. But this term here is a little bit hard to work with. So this is not, you can try to do this, and I'm pretty sure every approach I've seen trying to do this doesn't really get far. So a good approach is to instead factor this as y cubed is x plus I times x minus I. Okay, so we can make some quick observations. I guess one of the quick things you can see early on is that if you just consider parity and what are squares mod 4, and you get that x has to be even and y has to be odd. Right, because if x were odd, then this would be 1 mod 4 and this would be 2 mod 4, which is bad. So let's just write this on the side, x even and y has to be odd. Okay, so we do this factorization. And so the key claim now is going to be that x plus I and x minus I have to be relatively prime for this equation to hold. Okay, so this is a factorization over zi. So the idea is, if these are relatively prime, then think about what happens over the integers, right? If you have a perfect cube, which is the product of 2 relatively prime integers, then that means each of the factors has to be a perfect cube, right? Because they can't share any prime factors. So I'm going to claim that these are relatively prime. Then that means each of these has to be a perfect cube. So let's go on and prove the claim real quick. Claim GCD x plus I, x minus I is 1. Okay, so technically it can be any unit, but we just say 1 to represent some unit. The proof of this, so if P divides, so let's say there's some prime dividing both of them, right? But the only way it's not going to be 1 if there exists a prime that divides both of these. Then that means the prime divides their difference. And so P divides 2I. So if P divides 2I, then we take the norm of both sides, which means that norm of P divides the norm of 2I, which is 4. Okay, so that means norm of P is either 1, 2, or 4. Now, something you can show easily is that if it's 1, then that means P is a unit. So this is no good. So 1 is not happening. Okay, and 4 is not happening simply because by our classifications of primes, 4 is not possible. So that means the norm is in fact 2, and that means P has to be 1 plus I. But there's going to be some contradiction here, and in particular, if I scroll down a little bit more, what do I mean by norm? Good question. So the norm is by definition this n symbol here, right? So it's analogous to something like absolute value over the ordinary integers. It measures size in some way. So in this case, this is just the square of the length of the number a plus bi in the complex plane, right? And as I mentioned, ordinarily, if you were considering geometry, you would consider its square root. But because I want things to be integers, I square the length. So norm here is of a plus bi is a squared plus b squared. Okay, and all right, I'm running a little bit over time, so I'm going to try to hurry this up. This shouldn't take too much longer. So, so norm has to be 2. It's 1 plus I. Let's see. So I'm going to apply a similar trick again. So if P divides X plus I, then that means the norm of P divides the norm of X plus I. But because so X is an integer, then this is X squared plus 1. Yeah, so in this case, it's the same as modulus squared, the norm. Yep. Why is it that dividing P X plus I that the norm of one divides the other? Okay. Yeah. So this is follows from the sort of multiplicative properties of norms. And you can also just check it generically. If you have like A plus BI divides C plus DI, just write out both of your norms, you will see that divisibility implies divisibility of norms as well. Anyway, let's see, where were we? So yeah, this implies that the norm has to divide x squared plus 1. But from the original equation, x squared plus 1 is y cubed. And we said y is odd, so y cubed is odd. So we have the norm of p, which is 2, divides an odd number. So this is a contradiction. Okay, so this tells us that p does not exist. So in particular, that means the GCD is 1. Okay, that's what that means. So I'm going to scroll down a little bit more. So because we've now shown that they're relatively prime, that means each of the factors x plus I and x minus I must itself be a perfect cube. Well, up to a unit, right? You can always multiply by units, but units themselves are already perfect cubes, so we're not going to worry about units. So this means that x plus I is a perfect cube. So in the Gaussian integers, this is a plus bi cubed, right? And if I expand this, this would be something like real part a cubed minus 3ab squared plus I times 3a squared b minus b cubed. Right, and now we just match real and imaginary parts. So x equals a times a squared minus 3b squared, and 1 equals b times 3a squared minus b squared. Right, now remember, x, a, and b are all integers. Now this is where we use ordinary number theory over the integers. 1 is a product of two things, right? So that means b has to be plus or minus 1. And then, you take possibilities of b. So if b is plus 1, then 3a squared minus 1 has to be 1. There's no solution to that. If b is minus 1, then 3a squared minus 1 has to be, let's see, negative 1. And okay, I'm saying something wrong. Anyway, yeah, there's a solution to that, right? 3a squared minus 1 is negative 1. You have to take a is 0. That means the only solution is a, b is 0 minus 1. You can check that this satisfies the first. If you plug this into the first equation, this gives you x, y is 0, 1. So this is the only solution. So you can actually use the same method to solve the problem that was advertised in the description, which you can use the same method to solve x squared plus 2 is y cubed, right? You can imagine you factor over the ring z adjoint root minus 2. And because I'm telling you that's also a unique factorization domain, then you just run through the same arguments. You use the norm to rule out possibilities until you get a system of equations like this, and then you just solve from there. So yeah, I think we're a little over, so I guess I'll stop here for now. If people want to stick around, ask questions, I'm happy to answer questions. I could show this if you want, although that's going to take another like 5-ish minutes. Yeah, so we'll leave it here and we'll see if people have questions they want to ask. Oh, someone asked me what math drawing software this is. Yeah. So this is not a math software. This is just a pure drawing software. So this is a website called, let's see if I can, let me type this into chat. Where's the chat? If you're interested in using something like this, this is all attendees. co-create.cso.mit.edu. It's a program that one of our professors in the CS department made for their virtual classes. So that's the Blackboard program I'm using in the background. let's see, how did you determine that x is even and y is odd? Okay, so this is an important step. And the reason is because suppose the opposite were true. If x were odd, right, then x squared would be 1 mod 4. Because an odd number squared is always 1 mod 4. You can't get 3 mod 4. So that means 1 plus 1 is going to give you 2 mod 4. But then you want a perfect cube to be 2 mod 4, which is not possible. Right? 2 mod 4 means it's divisible by 2, but not 4. But an even perfect cube has to be divisible by 8. So it would be 0 mod 4. And so that's why x is even and y is odd. You can deduce a similar thing in this case, probably. Anyway, that's how you determine that. All right. Other questions? How do you prove that all irreducibles are prime? Good question. So, yes, as I mentioned, this is only true in a very special, only specific cases. There are actually not many rings for which this holds, which is why you're so special. The general way to do it is actually indirectly. So, as I mentioned, if you're studying number theory over the integers, say in a class or a summer program or something, you would to prove that all irreducibles are prime over the normal integers, you would probably use some variation of Bezout's lemma, right? And then that's a classic proof for the integers. For the Gaussian integers and other rings, it's much more tricky. And the way to do it typically involves more advanced math tools in abstract algebra. But I guess a simple way you might try to do it is to show that there exists some variation of the Euclidean algorithm, right? So the Euclidean algorithm is, over the integers is basically you state the division algorithm, and it sort of lets us find GCD of numbers by taking their differences and so forth. And there exists an analogous Euclidean algorithm over the Gaussian integers. It requires a little bit more work to prove that such existence is unique. But then there's a deep theorem that says that if there exists a Euclidean algorithm, then you're in a unique factorization domain. In fact, I guess let me just share a quick Wikipedia real quick. There's a unique factorization domain. If you go on Wikipedia for unique there's actually a whole chain of different types of rings you can get. So there's this whole chain of things. And there's some fancy words in here we're not going to worry about too much. So if we want to find these unique factorization, it's sufficient to prove it for any of these stronger conditions. I mentioned Euclidean domain means there exists a Euclidean algorithm. So this is one way of showing just there exists a Euclidean algorithm. One of the ways to show something called a principal ideal domain. Again, this gets into the issue of ideals, which I don't want to dive too deep into. But yeah, that's the gist of how that works. You generally don't prove this directly. Yeah, it's hard to prove directly. You do it by some other sidestepping way. Let's see. If people are still here, okay, I guess one last thing that's kind of important to show sort of for any algebraic number theory talk is when unique factorization fails. So for example, in z adjoin root minus 5, unique factorization fails because we can write 6 equals 2 times 3. This is sort of the prototypical example you see everywhere. It's also 1 plus root minus 5 times 1 minus root minus 5. And so this is sort of 2 completely different factorizations. And you can check that these are not associates of each other, right? Multiplying by units in one of these doesn't give you the other one. And you can also check that each of these is a prime element in the ring. So here unique factorization fails, and because you can sort of get the counterexample of that, you can produce an irreducible that's not a prime. And so the resolution in more advanced algebraic number theory is something called unique factorization of prime ideals. So this word ideal has been something I've been fully about and don't want to get too in depth into because it's a more heavy machinery. But that's sort of where you would go from here. What would be the name of a typical college course that would go into this type of material? Great question. So over the unique factorization of Gaussian integers is something you would probably see in the first class in what we call elementary number theory. So elementary number theory is basically the number theory most of you are already doing in competitions. The way to go further in this is something called algebraic number theory, which is basically using tools from abstract algebra applied to number theory. Right? So the notion of a ring is a very important concept in abstract algebra. And you can study all sorts of rings that are not number rings. Like these are all examples of rings applied to sort of concrete numbers. But in abstract algebra, we study all sorts of exotic rings with, let's say, more variables, and then you can sort of take mods by exotic combinations. That's why this condition is here, that all elements can be written as a product of finitely many irreducibles, because in more advanced abstract algebra, this isn't always the case. If you want a keyword to look up, you would look up Noetherian ring, named after Emma Noether, Noether. How did you solve for A and B? Okay, so to solve for A and B here, this is where we use ordinary number theory over the ordinary integers, right? The point is we're trying to solve this over the integers. So X and Y are integers, right? And so are A and B. So X, A, and B are integers. So the second equation says one is a product of two integers. That means the bottom things here, that means this is either 1 times 1 or -1 times -1, right? That means B is either plus or minus 1. If B is plus 1, you get no solution because you need to solve 3a squared minus 1 is 0, right? Let's just write this out to be concrete. You can either have 3a squared minus 1 is 1, or 3a squared minus 1 is -1. Right, so the first equation has no solution over the integers. The second equation just takes b a is equal to 0. And that's how you solve for A and B. Okay? And if you do something similar for the, you could treat this as a take-home exercise if you're interested. You get something similar. This one will be a 2 instead. So you get more possibilities, which is why if you want to check your answer to this, the solution for this is going to be like xy is what is it? It's like 5 and 3, plus or minus 5 and 3. Right. And so that's sort of the obvious solution you would find if you're just sort of guessing and checking. And it requires these sort of fancy tools to prove that they're actually the only solutions. Great. Other questions? All right. I guess if not, well, I guess thanks everyone for coming. I'll be actually part of the what's it called? HMMO organizing panel starting at 4. If any of you want to listen to me talk more about just organizing in general. Yeah, thanks for coming. And yeah, I think that's it.
All right. Thank you so much, Jeffrey, for that really good talk. So yeah, like Jeffrey said, there's going to be this is the end of like the class section of education. And later, starting at 4, there's going to be some panels. So you can look at, again, link.hmmt.org/catalog for those list of panels. And then hopefully we'll see you there. So yeah, have a great rest of the day, and we hope to see you at the panels. Thank you.